Hello everyone, this is lecture 3 in week 8. Recall that in the last two lectures we were learning about the augmented Lagrangian method. So we learnt about the differences between quadratic penalty method and augmented Lagrangian method, right, or how to get the augmented Lagrangian method by modifying the quadratic penalty method when you have only equality constraints. And in the last lecture we also learnt about how to handle inequality constraints. So that had more differences when you compare it with quadratic penalty method, right. So so we will continue. I will work out an example which has only inequality constraints, right. So if you recall what we were seeing in the last class, so we derived the augmented Lagrangian function L gamma, which is a function of x, lambda and mu, which is as given the top of your screen, right. And if you recall, this is actually for optimization problem that is given here, right. So you are minimizing f of x subject to both, you have a bunch of inequality constraints as well as equality constraints, right. So when you have them, this we derived this to be the so the L gamma that you see here, right. So that we derived it to be the augmented Lagrangian function, right. So we will first derive the gradient and Hessian of this function, since we are actually going to so when we are using this algorithm, we are we will need the gradient and Hessian anyway, because we are going to minimize this augmented Lagrangian function in an unconstrained fashion, right. So if we use Newton's method to minimize this, we need the gradient as well as the Hessian, right. So we will first write down the expressions for the gradient and the Hessian of the augmented Lagrangian function. So the gradient of L gamma x lambda mu is del f of x plus summation lambda j del hi j of x, summation from j equal to 1 to m. And now for hi j you will have 2, so you will have 2 everywhere, so I will pull the 2 outside. So you will have hi j of x del hi j of x, where j runs from 1 to m, and so here note that mu I squared by 4 gamma squared does not depend on x. So this gradient I am taking with respect to x. So this term vanishes when you take the derivative, right. So we just differentiate this, and so here again we will have 2, which I have pulled it out already. So we will have summation I equal to 1 to p. So we will have this term as such, max of 0 g I of x plus mu I by 2 gamma, and we will have to differentiate this, for which we will have del g I of x, right. So it is easy to see that this is actually differentiable, though we have the max component. So that is because if you have j of x plus mu I by 2 gamma to be less than or equal to 0, you will put 0, right, and if you put greater than 0, it is just j of x plus mu I by 2 gamma, right. So when j of x plus mu I by 2 gamma is equal to 0, right, so this term becomes 0 irrespective of whether you have this max term or not, right. So no issues. The gradient of L gamma of x lambda mu is well defined, and it exists when g of x plus mu I by 2 gamma is equal to 0, right. So it is the same as how we had it for the quadratic penalty function, right. Now about the Hessian, right. So let us write down the expression for the Hessian of the augmented Lagrangian function. So we will have the Hessian of f of x plus summation lambda j into Hessian of Hj of x summation over j equal to 1 to m, and for 2 gamma here. So this will have two terms. So one term is Hj of x into Hessian of Hj of x plus del Hj of x into del Hj of x transpose, right. So all of this is the summation j equal to 1 to m. Okay. So now we will have to differentiate this, right. So yeah, this bracket is still open, please note that. Now here the first term is simple, you just write summation over I equal to 1 to p max 0 j of x plus mu I by 2 gamma and into Hessian of j of x. Okay. But the other term will be the following. So yeah, I can open this summation outside, and here we will have so if j of x plus mu I by 2 gamma were greater than or equal to 0, then we will have del j of x transpose. So this bracket for 2 gamma closes here. Okay. So of course the Hessian here as well has a problem. You can see that when gi of x plus mu I by 2 gamma is greater than 0, we will have del j of x into del j of x transpose. When it is less than 0, we won't have it, but at equal to 0, yeah. So the left hand side derivative of del L gamma and the right hand side derivative of del L gamma are different. So the Hessian actually does not exist when gi of x plus mu I by 2 gamma is equal to 0. Okay. So that is true, but nevertheless when you work this out, this works for many of the problems. So yeah, we will continue using it. I mean, we did that even when we had worked this for the quadratic penalty method, right. So but nevertheless we were able to use Hessian for many of the problems, so we can continue doing that here as well. And now that we have written down the gradient as well as the Hessian, we will start working out an example, right. So we will again work out an example where you have only inequality constraints, right. So we will work out a problem which we already solved. So if you see here, we have this particular problem where we are minimizing the distance from the point 3, 2 subject to the feasible set being a triangle with vertices 0, 0, 1, 0 and half half, right. So we will work out the same problem in augmented Lagrangian method, right. So possibly I will write down the problem here more clearly. I will write down the problem here more clearly. Half of, we are minimizing over x1 x2, half of x1 minus 3 the whole squared plus x2 minus 2 the whole squared, subject to the constraints such that the following constraints hold: minus x1 plus x2 less than or equal to 0, and x1 plus x2 minus 1 less than or equal to 0, and minus x2 less than or equal to 0. So yeah, I have just copied down what we had here. Sorry. Yeah, so I have just copied down what we had here. So x1 greater than or equal to x2 becomes minus x1 plus x2 less than or equal to 0, and yeah, x1 plus x2 minus 1 less than or equal to 1 and less than or equal to 0, and minus x2 less than or equal to 0. So that is what I have written down here. Okay. So fine, we will and recall that the answer was 1 comma 0, right. So, we will try to solve this problem using Python now. So, yeah, so this is a problem that we have solved earlier. So, we will take up f, g and grad g from this that we have already used, right. Okay, so yeah, I can also import numpy, that will be required, and yeah, so and we can also include the name. Yes, this is augmented Lagrangian this is augmented Lagrangian method for inequality constraints. Okay, so yeah, we have defined the function which is half x1 minus 3 the whole squared plus half x2 minus 2 the whole squared, and the constraints minus x1 plus x2 less than or equal to 0, x0 plus x1 minus 1, x2 minus 1 less than or equal to 0, and minus x2 less than or equal to 0, and this is the gradient. Now we will yeah, copy this down. So, since this was the augmented Lagrangian method for equality constraints, so we will copy this down and change it. The augmented Lagrangian function, its gradient, Hessian, and the code, right. Okay. So, of course, these, I mean, there needs to be a change here as well. So, L gamma, if you recall the function, yes. So, yeah, we do not have h because there are no equality constraints. So, after f of x, we need to write this down. So, yeah, since we have squared here and squared under summation, we will write them as dot product of the vectors, right. So, we will do that here as well. So, we have f of x plus, yeah, so you will not have this, but here we will have max of 0 comma gi of x plus mu I by 2 gamma, right. So, yeah, we will write it as follows. We will write g of x plus gm by 2 gamma greater than 0 multiplied by, yeah, g of x plus gm by, oh, I am sorry, mu by 2 gamma. So, it just be m by 2 gamma. So, this also has to be m by 2 gamma. Okay. So, we will give a bracket here. So, this will actually give us g of x plus mu by 2 gamma if it is greater than 0, otherwise it will give us 0, right. So, this Boolean function is something that we are already familiar with, and instead of L we will have to use m because this is mu. Okay. So, yeah, and yeah, we will have to use the same thing here. So, this does this particular part, max of 0 gi of x plus mu I by 2 gamma the whole squared summation. Now, we also have this summation minus mu I squared by 4 gamma squared, right. So, I can do a dot product here as well. We will do m dot m which is summation mu I squared by 4 gamma squared, by 4 gamma squared. Yeah. So, this is so what I have written now, what I have now done is by I have written down L gamma, right. So, we will now write down the gradient. So, the gradient of f of x is x0 minus 3 and x1 minus 2. So, we will write that here, np dot array of x of 0 minus 3 and x of 1 minus 2. Okay, and here again we will have to make a change, which is so the del h parts can be scored out because there are no equality constraints, but we will still have this set of constraints, so we will write that down. So again we will use this term, so we will have 2 gamma, so we can remove this, and for 2 gamma we can use this straight away, and we matrix multiply with grad g of x. Of course, I have to write m here. Okay, so I have just done 2 gamma into, so this is max of g of x plus mu I by 2 gamma comma 0, and you are multiplying that with the grad g of x matrix. Okay, and so for the Hessian, the Hessian of f is identity matrix I of 2, and here again we will have to write down all of this. So h can be scored out because we do not have equality constraints, but and similarly the Hessian of gi's can also be scored out because the constraints are linear. So the Hessian is 0, so you only have to have this, right. So we will write this down when gi of x plus mu I by 2 gamma is greater than or equal to 0, right. So again we can 2 gamma remains outside, and so we can have this, so we should have grad g, and this is grad g as well, so you change this as m. Okay, and x is 2 dimensional, so we have 2 zeros, and m is 3 dimensional because we have 3 constraints, so we have 3 zeros. Gamma and k, gamma is 1 and k is 0, and these constraints remain the same. L's have to be modified into m's. We will do them. And so here as well we can write this as x. So x is 2 dimensional, so we will cancel this. So since this is 3 dimensional, I will put this here. Okay, and so m here has to be modified. So m plus 2 gamma g of x, and so again if m is greater than m, then it is m, otherwise it is 0. So that is something we will have to change as well. And here we have this as mu. Mu is, there are 3 components, so and this is m. And here as well I need to modify m. Okay, so just going through the code, I have just defined f of x to be half of x1 minus 3 the whole squared plus half of x2 minus 2 the whole squared, g of x by these 3 constraints, the gradient of g, L gamma gradient, and the Hessian. So this code is just what we have here. So the initializations, what I have written down as algorithm, initializations we have, there is a loop that is going on. In each loop we are actually finding the minimum of the augmented Lagrangian function when lambda k and mu k are constants, and after that fixing x as constants we modify lambda and mu, right. So this loop goes on, and whenever the augmented Lagrangian function is close to the actual function value, then we stop. So that is exactly what we are doing here. So let us check if this works. Okay, so since I have put 0 comma 0, I need to, it is a feasible point. So I need to add k equal to 0. That's the first step. Sorry, k equal to 0. Yeah. Okay, so I think I missed a comma here. Okay. Yeah. Fine. So you can see that x is 1 comma 0 and mu is 0 comma 2 comma 0. Okay, so this is something that we did not calculate. Yeah, but it can be checked, not a big issue, right? So the answer here turns out to be mu star is 0 comma 2 comma 0. Okay. Yeah, verifying this is not very hard, because I mean, if you write down, if you recall how we solve constraint optimization problem, right? So we write down the Lagrangian, not the augmented Lagrangian, I mean, don't get confused, right? So the Lagrangian would be half x1 minus 3 the whole squared plus x2 minus 2 the whole squared plus lambda 1 into minus 1 plus x2 plus lambda 2 into x1 plus x2 minus 1. Okay, maybe I write it as mu 1, because that is how we write for inequality constraints, right, minus mu 3 x2, right. So if you write down the KKT conditions, right, so we will have 2 in x1 minus 3 plus or minus mu 1. So I am just differentiating this with respect to x1. So we will have minus mu 1 plus mu 2 equal to 0, and if you differentiate with respect to x2, you will have x2 minus 2 plus mu 1 plus mu 2 equal to 0, right. And the other so that is just the derivative of the Lagrangian that I have written here with respect to x. So the other constraints are that, of course, these three constraints have to be satisfied: minus x1 plus x2 less than or equal to 0, x1 plus x2 minus 1 less than or equal to 0, and minus x2 less than or equal to 0, right. So and other than this, we yeah, of course we will need mu's to be greater than or equal to 0, and yeah, we also have complementary slackness conditions where mu 1 into minus x1 plus x2 equal to 0, mu 2 into x1 plus x2 minus 1 equal to 0, and mu 3 into minus x2 equal to 0, right. So you can check that, I mean, yeah, you can solve this, that is because these set of conditions form the KKT conditions, right. So you can solve this and check that this is going to be the solution, but the other way is you can substitute this to check if it works or not, right. So you can see that the first equation is satisfied because mu 1 is 0 and you have 1 minus 3 plus 2, that is 0, and similarly here mu 1 is 0, so we have 1 minus 2 0 minus 2 plus 2 is 0, right, and minus 1 plus 0 is less than or equal to 0, 1 plus 0 minus 1 is equal to 0, and this is also equal to 0. You can see that mu's are all greater than or equal to 0, and since minus x1 plus x2 is non-zero, it is actually minus 1. So mu 1 has to be 0, as you can see that mu 1 is 0, and x1 plus x2 is equal to 1, so that means mu 2 can be greater than 0, it is greater than 0 here too, and x2 is also 0, so mu 3 is greater than or equal to 0, but it happens to be 0 here, okay. So yeah, of course we this is just to justify that the Lagrange multipliers that we have here 0 comma 2 comma 0 are actually the correct Lagrange multipliers that we have here, right. And yes, so yeah, that's, you can say, one advantage of the augmented Lagrangian method. So you not only get the solutions x1 x2 dot xn, but you also get the Lagrange multiplier values lambdas and mu's, right. So all right, So, this is for when you have a problem with only inequality constraints, right. So, in the forthcoming lecture we will actually work out some practical examples, right. So, if you recall in the very initial lectures we gave a few practical examples, but I mean we left it over there because they were you can say constraint optimization problems, and we were looking for unconstrained optimization problems for a long time, right. So, now given that we are actually working on constrained optimization problems, it is time that we look at those problems. Okay. So, in the next lecture we will work out one of those examples and solve them using solve it using the augmented Lagrangian method. Thank you.